Homework number 4 is due a few days from now. It's on the 20th. That's a Thursday. That's a different day than you're normally turning things in. And I've posted some notes on how you might be able to mechanize this process of finding eigenvalues and eigenvectors without using the determinant. Since we are going to wait until the end of this book before we start talking about a determinant, since this is linear algebra done right, we're trying to understand some of these concepts prior to just generically saying, oh, here's a determinant. Don't worry about what it means or how to, well, we would have to worry about computing it, but finding the roots to find our eigenvalues. Here we're doing that a different way by essentially solving these sets of equations or coupled equations sort of in steps to allow us to find this nth order polynomial, and that's what's in lecture 4.2e. It's not really a lecture so much as it is notes that give you a little bit more specific detailed information about this recipe for computing eigenvalues and eigenvectors. Again, we're in chapter 5. I guess I didn't have to tell you that if you look at what theorem numbers and our corollaries are, but we want to finish an earlier example where we were illustrating a particular linear map or operator that didn't have real eigenvalues. I think we got through the non-real eigenvalue solution or the non-real solution to our second order equation, and then we will start stepping through some other results from chapter 5. Namely, if you have distinct eigenvalues, then those actually correspond to linearly independent, or that provides you with a set of linearly independent eigenvectors. And we know what we can do with linearly independent vectors in terms of forming basis or starting to create these basis vectors that we want to. The number of distinct eigenvalues, maybe this is obvious, is less than or equal to the dimension of our vector space, capital V. And so if we say that our vector space is n-dimensional, it's finite, then we know that we can't have any more than that in terms of distinct eigenvalues. And here distinct means that you could have a pair of complex conjugate eigenvalues. Those are distinct since they are living. One is the conjugate of the other. Those are distinct eigenvalues. We will talk about creating more complicated functions of these operators, and one that's used quite often is this matrix exponential, e to the a, and we will talk about that. And then we will make it a fact or a theorem that every operator on a finite dimensional complex vector space of a non-zero dimension has an eigenvalue. If we get that far, we will start talking about upper triangular matrices. This is a recap of where we've already been. You should have this equation memorized and commit it to memory for the rest of the semester, if not longer. And that is, if we are dealing with eigenvalues and eigenvectors, we really are starting to think about invariant subspaces, where these eigenvectors are associated with invariant subspaces. You now, maybe you're living on this eigenvector, or you have a vector that's in the direction of this eigenvector. If you now map that through this linear operator t, you're going to get back on or stay on that same vector. So it's invariant to this linear operator, capital T. And we call the W vector that satisfies this equation the eigenvector, and the scaling amount we call the eigenvalue, or lambda. Here's our example from earlier. And I will actually try to fit it all on one screen, and so you can see it in mass for the sort of the first case. Well, maybe I haven't gotten there yet, but here is the linear map, which if you think about it, it's on a 2 vector, and the vector is now w1, w2. If you envision what's happening when you pass w1, w2 through this linear operator, it actually is similar, or it is, a 90-degree counterclockwise rotation in the xy plane. If you view this linear map operating on a vector on an xy plane. Which then says, if we try to determine the eigenvalues associated with this linear operator, we would be saying that the output of that operator, which is minus w2, w1, needs to equal a scaled version of the original vector, which was w1, w2. And I've just rewritten that in the middle of the screen in that blue equation. Once we have that relationship, we can look at the 2 different coordinates. And if this was a higher dimensional problem, we would be looking at all of the coordinates to try to find a solution or values of w1, w2 up through wn and lambda that satisfied that relationship to establish eigenvalues and eigenvectors. Here, if we look at the first coordinate, we see that minus w2 needs to equal lambda w1. We can solve that for w sub 2 by multiplying both sides by minus 1. We then pull off the second coordinate, which is w1 is equal to lambda w2, and use our expression for w2 in the second equation to allow us now to find one equation in terms of w1. And we want that equation to be true for any value w1, and that now says that what's preceding w1 on the left, which if you explicitly identify it, that's 1 for its scalar, that now equals minus lambda squared if this is true for all w1. And that's what I've now indicated in the blue box. But if we restrict our lambdas to only being real numbers, we can't find a number, a real number, which when it gets squared becomes negative. That's just not how we have worked with real numbers, and so this has no solution when we restrict our field of numbers. This particular eigenvalue eigenvector equation from this linear map does not have a solution when we restrict our scalars to be real for the eigenvalues. And that really is saying that we do not have any invariant direction. If we're rotating in the xy plane, then that means we're not returning to where we started. If we started on the x-axis and the linear map puts us up on the y-axis, that's not the same direction as the x-axis. So that direction that we started is not invariant. And that's one way of thinking about this not having a real solution, is the fact that this particular linear map is corresponding to a 90-degree rotation in the xy plane. So let's look at what happens when we deal with our field being the complex numbers. Now we can look at lambda squared equaling minus 1. Now we've opened up this number field to be bigger. Lambda now can be a complex number, so that this now says that lambda is plus and minus j, where I'm saying j is my square root of minus 1. And now if you wanted to think about that visually, maybe you might be thinking of a complex plane where you have the real axis and the imaginary axis. This particular linear map corresponds to having eigenvalues on the imaginary axis. No real part, and plus j and minus j for the eigenvalue. or eigenvalues, and those are distinct eigenvalues. What about the eigenvectors? Now what we do is we look at each particular eigenvalue in the equation, the eigenvalue-eigenvector equation. Let's now look at the case where we have our eigenvalue in the upper half of the complex plane. Let's say it's plus j. Now we have our eigenvalue-eigenvector equation, which was minus w2, w1. That was the output of the linear map on a vector w1, w2, and that was supposed to equal lambda times the vector that we started with, which was w1, w2, or if we put all of that in, or we push that j into the vector, now we have j omega 1 and j omega 2, and what's on the right needs to be the same as what's on the left. And if you look at each of these coordinates, maybe you have to do some multiplication by j's, but you'll see that those two coordinates give you a consistent relationship. It's the same relationship in the first coordinate as is the second coordinate. In the first coordinate, we have minus omega sub 2 equaling j omega 1. And we could say then that if we say omega 1 is our free variable, let's solve for what omega 2 needs to be in terms of omega 1. We can multiply both sides by minus 1, and we have omega 2 is equal to minus j omega 1. Which now says that our eigenvector that's associated with that eigenvalue that was in the upper half of the complex plane, which was plus j, let's say that we call that eigenvector, since it's in the positive half or positive y direction or vertical direction in our sort of xy or complex plane, let's just call it w positive, is now proportional or directionally the same as omega 1, and the omega 2 coordinate we just found what it needs to be. It now needs to be minus j omega 1. Where we can pick omega 1 to be a complex number, and now we have this omega plus, that's now our eigenvector for lambda equal, or for our eigenvalue in being plus j. And you might try to see this, but it's probably easier to start thinking about this w plus as having a real part and an imaginary part, and each of those give us sort of a directional information as far as the invariant subspace associated with these complex eigenvalues. We can also find the eigenvector for the other eigenvalue using exactly the same approach. Again, we have exactly the same output from our linear map, that's minus w2, w1, but now that's equal to minus j, since that's now our eigenvalue, times where we started, or the original vector, which was w1, w2, and this is now minus j omega 1 minus j omega sub 2. Again, we can see that we have consistency between the two different coordinates, and we can now say that minus, the first coordinate says minus w2 is equal to minus j w1, or in fact W2 is equal to J W1. And now we have the eigenvector that we can associate with the eigenvalue that was in the negative, or the bottom half of our complex plane at minus j, right on the imaginary axis. And we could call this, let's say, w minus. W1 maybe is our free variable, so we just put W1 as some value, and W sub 2 is now JW1, and we want to keep, or we can consider, W1 being in the field of complex numbers. And this is now our second eigenvector associated with that linear map, and the only way that we were able to find eigenvalues and eigenvectors for this linear map that started as a 90-degree counterclockwise rotation, if we just looked at it as an xy plane or operating on a point in the xy plane, that now didn't have a real eigenvalue, and so it didn't have any eigenvectors. But if we expanded that to be the field of complex numbers, we were able to identify these conjugate eigenvalues of plus and minus j. No real part, but purely imaginary. That's going to conclude our example. Let's now get into some of these facts or relationships on into Chapter 5, and in particular, let's look at Theorem 510, which is talking, or titled now, Linearly Independent Eigenvectors. This theorem then says the eigenvectors associated with distinct eigenvalues of our linear operator are linearly independent. Is it clear what I'm meaning by distinct? I tried to talk about that before, but if I gave you a set, let's say -1, -2, -3, -1, are those distinct eigenvalues? No. What about -1 plus j, -1 minus j minus 2? Distinct or not distinct? Those are distinct. They're conjugate, but they are, if you sort of plotted those in the two-dimensional complex plane, those points which are representative of the eigenvalues are not on top of each other. So that's what I'm meaning by distinct eigenvalues. If we have distinct eigenvalues, then the eigenvectors associated with each of those eigenvalues is linearly independent. Question. What about +1 and -1? Are those distinct? Are they in a separate point on the complex plane? So this particular set, -1, +1, they are distinct. Maybe what you're uncomfortable with is that +1 being in the right half plane. You've maybe grown fearful of having eigenvalues that are in the right half plane. In a control setting, that's kind of not where you want them, but it's okay. It's a distinct eigenvalue, so if we found the eigenvectors associated with -1 and +1, they would be linearly independent eigenvectors. Not necessarily orthogonal. I might sort of indicate orthogonality, but they're just linearly independent eigenvectors. Let's look at showing that in the form of a proof. First, we're starting with t being a linear operator, and that's how we represent it, or put it in a symbol. And now let's make an assumption. Let's assume that we have m Michigan distinct eigenvalues. I'm going to say that we have lambda 1, lambda sub 2, lambda sub m distinct eigenvalues. And I now know, or you've convinced me that you know what that means. That means that we can associate with each of those a particular eigenvector, v1, v2, v sub m. So the eigenvector associated with the eigenvalue lambda 1 is v1, etc., up to m. And what the theorem is saying is that if we now collected those vectors, v1 through v sub m, that would form a linearly independent set. It doesn't mean that they are a basis, because we may not have all of our n Nevada eigenvalues distinct. But if we have m distinct eigenvalues, then we are assured that the eigenvectors associated with those m are linearly independent. That's what I'm indicating here. M, Michigan, is less than n, or less than or equal to, where n is the dimension of our vector space. Let's now prove this, that those m eigenvectors associated with the m distinct eigenvalues are linearly independent. And let's do that by contradiction. If we're proving it by contradiction, we need to assume something isn't true, and what we're going to assume is not true relative to the theorem. The theorem said that v1 through vm are linearly independent. Let's go ahead and say that they're not. And then we'll hopefully find a contradiction in our argument, and then we'll be able to conclude, oh, our assumption was wrong, so they have to be linearly independent. Let's start then with assuming v1 through v sub m, that set is linearly dependent. And you now know what you can do with that, what you can do. Maybe that's not the right way to say that. You might do a lot of things with a set of vectors that are independent or dependent, but now that you have a set that are linearly dependent, what do you know that means? Did everybody catch that? That means that if you looked at any of these, some of those might be in the span, or one of those at least is in the span of the others. Or we can linearly combine these and have non-zero coefficients and still end up with the zero vector. There's a lot of ways of sort of showing that those vectors are linearly dependent. So this means, or one way to interpret this is to say that this means at least one eigenvector . in the above set. You could say, well, you didn't say it was in that set. So here, one of the m eigenvectors, v1 through v sub m, means at least one eigenvector in the above set is in the span of the others. Now let me get a little bit creative with how I represent that. Let me say that, let's let this integer L be the smallest integer such that v sub L is actually in the span of v1, v2, up to v sub L minus 1. So we've shuffled these eigenvectors and we've ordered them v1, v2, v sub whatever, such that when we're counting up all of these or putting them in the right order, when we get to L, which might be 6, then it's in the span of v1 through v5. We've just ordered this m, maybe m is 10. But L is now the smallest integer such that we have this condition on it being in the span of the preceding L minus 1 eigenvectors. If that's the case, then that allows us to write this in a special way, doesn't it? It means that we can say that v sub L is a linear combination of v1 through v sub L minus 1. And this, now you're understanding why we spent so much time learning about linearly independent, span, etc. This means we can write v sub L as being equal to a1 v1 plus a sub 2 v sub 2 plus a sub L minus 1 v sub L minus 1. But this theorem had a linear map or a linear operator to it, t. So let's now apply that linear operator to this equation or both sides of this equation. Let's apply t, the linear operator, to both sides. You know this equation is true, and now we can say that we have t, v sub L, is equal to, and I'm going to pull out the coefficients and put them first on the right-hand side. I'm going to say a1 t v1 plus a sub 2 t v sub 2, etc., plus a sub L minus 1 t v sub L minus 1. But we assumed that these v's were eigenvectors, and now we can rewrite this equation in terms of scaled versions of those vectors. Since t v1 is lambda 1 v1, t v2 is lambda 2 v2, t v sub L is lambda sub L v sub L on the left. This gives us now what I'll call equation 1. On the left, we have lambda sub L v sub L. That's just the eigenvalue-eigenvector relationship, which we said these v's are associated with the appropriate lambdas. Then we have a1 lambda 1 v1 plus a sub 2 lambda sub 2 v sub 2. And we just keep finding different eigenvalues as we go down the right-hand side. We're able to write equation 1. Let me just say why. If you're going back through your notes and you're going, I have no idea what he just did or what was just done, This is because TV sub I is lambda sub I, V sub I, and those V sub I were actually eigenvectors. But we can come up with a similar looking equation based on our starting with what V sub L was equal to. Remember, V sub L was this linear combination of preceding eigenvectors. If we use that, let's say we now have V sub L is equal to A1 V1 plus A2 V2 plus A sub L minus 1 V sub L minus 1. We can now create a second equation by, let's just hit that both sides by lambda sub L. On the left we have lambda sub L V sub L, and on the right we have A1 lambda sub L V1 plus A sub 2 lambda sub L V sub 2. Notice that I now am not changing lambda. It was the same across both sides. Plus A sub L minus 1 lambda sub L V sub L minus 1. That was provided or possible by multiplying by lambda sub L. And what I want to do now is combine equations 1 and 2. By combine, I want to subtract equation 2 from equation 1. And that will give me a 0 on the left-hand side, because the left-hand side is the same on both equations. If I now combine, unfortunately I'm going to have to scroll, but remember what equation 1 equals. You have it on your notes. Let's now combine 1 and 2, and by combine I'm subtracting to give us equation 3, so that I now have 0 on the left, and on the right I have a constant that's, or a coefficient that's the same in the first element, that's A1, but I now have equation 1 had lambda 1, equation 2 had lambda sub L, and that now gets scaled, or is scaling V sub 1. Plus A sub 2, lambda sub 2 minus lambda sub L, V sub 2, plus all the way down to A sub L minus 1, lambda sub L minus 1 minus lambda sub L, V sub L minus 1. And now we can go back to our earlier assumption on how we arranged these V's. Remember, we put these V's in a particular order, or in a sort of pattern. And what do we know about vectors V1, V2, up to V sub L minus 1? Or what do we know about V sub L? V sub L was in the span of these, and V sub L was the very first vector to be in the span of the preceding vectors. That means that these vectors are linearly independent. So by assumption on V sub L. So because V sub L was the first vector that could be written in terms of the earlier vectors, the list v1, v sub 2, v sub l minus 1 must be linearly independent. What does that imply with equation 3? The linear combination of v1 through v sub l is equal to 0. And v1 through v sub l minus 1 is linearly independent. That says that their weights or scalings have to all be 0 if they're linearly independent. Therefore, equation 3 implies all the coefficients are 0. That is a1 lambda 1 minus lambda sub l is equal to 0, etc. A sub 2 times lambda sub 2 minus lambda sub l is equal to 0. But we could make that happen many different ways, couldn't we? But let's just look at, well, we can look at really two different ways that that could happen. Therefore, the first way is either the lambdas are the same, which means that lambda 1 is equal to lambda sub l. Either there are and that would mean that those eigenvalues are no longer distinct. So either there are non-distinct eigenvalues, but that contradicts our first assumption. There's one of our contradictions, or at least we've come to a contradiction for that path. That's good. Or another way that those coefficients or scalars could all be 0 would be if all the a sub j's are 0. Or all the a sub j's are 0. But remember how we created those a sub j's to begin with. But v sub l was actually equal to a1 v1 plus a sub 2 v sub 2 plus a sub l minus 1 v sub l minus 1. And if all the a's are 0, what does that tell us about v sub l? It's the 0 vector. But we didn't choose v sub l to be 0, did we? So that's a contradiction. So, but v sub l being of this would imply v sub l is equal to 0, and that path produces a contradiction. And now, that's what we were trying to show, proof by contradiction. We ended up with a contradiction on the different paths by assuming that our vectors v1 through v sub l minus 1 were linearly dependent, and they can't be. Therefore, this list v1, v2, v sub m must be linearly independent, which is what we were trying to show. What did we just conclude? Or what was that theorem? That's what you probably need to remember. That if we have distinct eigenvalues, then their eigenvectors are linearly independent. That's a pretty strong result. Another result that we want to be familiar with is corollary 13 in chapter 5, which is dealing with the number of eigenvalues and that corollary says that if we have a linear operator T on a vector space V, that linear operator cannot have more than dimension V distinct eigenvalues. And I'll let you study that one on your own. But now you know that if you have a vector space of dimension Nevada, you can't have Nevada plus 1 distinct eigenvalues. Let's now look at another property of these linear maps that we're restricting to linear operators, and that is this idea of powers, polynomials, and functions of these operators. Since an operator is a map from a vector space to itself, then it's okay if we continually apply that linear map to previous outputs of that linear map. We're always going to get mapped back into the same vector space. So repeated applications of this linear map or linear operator, repeated applications are well defined. For T, being this linear operator on a vector space V, we'll define T to the M. So M operations of this linear operator will be T times T times T, where we do that M times. And that makes sense, since we're going from the input vector space when we operate on a vector in the input vector space, these operators return us back into that input vector space. That is our output vector space. Let's also then say that if we raise this linear operator to the 0th power, we'll define that to be the identity map. And now that we have these powers of linear operators, we can start associating those essentially with polynomials. With this, we can define polynomials of operators. By that, I'm meaning that if we have this polynomial p of z, which is a sub 0 plus a1z plus a sub 2 z squared on up to a sub m z to the m, and so I've really buried, but that's a sub 0 z to the 0 if you wanted to think about it, and that might be helpful when we're translating these polynomials into polynomials of operators, to have that placeholder z to the 0 there. Then we can write a polynomial of our linear operator, t, is now going to be a sub 0 I plus a1t plus a sub 2 t squared on up to a sub m t to the m. So you give me a polynomial, I can now create a polynomial operator with that polynomial. And once we have polynomials, we can actually go a little bit further. We can even start talking about more complicated functions of operators. Meaning, suppose that we're given some generic function f of z, and I'm just going to, instead of calling it a generic function, let me say that given f of z is some complicated function, then we can actually equate f of that complicated function as a polynomial of that operator. Where p of z is, let's say, the Taylor series expansion of f of z. So if you give me some complicated expression or function, I'm going to try to rewrite that as a polynomial expression, and I can generate that polynomial expression to approximate that complicated function by means of a Taylor series expansion. So we're still, the question was, are we no longer in a finite dimensional vector space? We're still having these linear operators on a finite dimensional vector space. So this complicated function may be weird, but we are actually going to, and it may be what do I want to say, infinite dimensional, but we're going to now approximate that with this Taylor series expansion in a polynomial sense. So we can make the approximation as close as we want by looking at more higher powers of this polynomial. Yes? Correct. So just because we have our linear, the question or the statement was just because our linear operator or the vector space is finite dimensional, it doesn't mean that this expansion has to be limited to a finite number of terms. But you can start to show with Cayley-Hamilton, but we haven't gotten there, that you can write this as a polynomial in a finite number of terms. Let's not go too much further down there, but let's look at what this might look like for a particular complicated function. As an example, suppose that we're given a linear operator t, and maybe somebody says, oh, I'm interested in my pet complicated function f of z is e to the z. But at this point in your educational mission or path or journey, whatever, however you want to call it, you know the Taylor series of this exponential. E to the z we can write as 1 plus z plus z squared over 2 factorial plus z cubed over 3 factorial, and that pattern just continues. That allows us then to express this exponential of our linear operator e to the t has that same structural pattern. Instead of the 1, it's now I. How big is I? So it's the same, it's operating on the same vector space as t, so whatever t is in terms of its dimension, I is now this square matrix of that dimension, or square map. Plus t plus 1 over 2 factorial t squared plus 1 over 3 factorial t cubed, etc. And that matrix exponential is used in a lot of different places, so it's nice to know that it is available to us. So this is used heavily let's say in advanced topics, if you can consider control advanced. I'll just say it is. So now you can talk about or use this in a control setting, in quantum mechanics, etc. Let's look at another fact or theorem associated or coming to us from Chapter 5, which Chapter 5 is Eigenvalues and Eigenvectors. Let's now look at Theorem 521. And that says that every operator that's T, that's an element of L of V, every operator on a finite dimensional and the next word is critical, complex vector space. Now we are working over the field of complex numbers. We're not just using F to mean real or complex. We are restricting this to complex vector space, and I might abbreviate that finite dimensional CVS, and don't forget the FD in front of that, or you might go down to the corner. Sorry. Isn't that one of the names of... Okay. Thought maybe I was completely losing it, but of a finite dimension, or I'm sorry, of a non-zero dimension is what I should say, because I've already said the finite. So every operator on a finite dimensional complex vector space that's non-zero has an eigenvalue. That says that you give me any linear map, if it's on a complex, finite dimensional complex vector space, it's going to have an eigenvalue, that linear map. How can we make that conclusion? Well, let's just prove it. So let's say that we're given a complex vector space V, where the dimension of that complex vector space V is little n, and we're assuming that n is strictly bigger than 0. So it's non-zero. We also have a linear map or a linear operator T, and now let's just select a vector V that belongs to that complex vector space capital V. So let's now arbitrarily choose a V in our complex vector space V, and let's make it not be the 0 vector, so it's non-zero. What if I create the following list? V, TV, T squared V, on up to T to the N V. What do we know about the dependency or independence of that list? Do we know anything? Can we make any conclusion? V was arbitrary, but it's non-zero. We now are operating on that by a linear operator T that's Nevada dimension. How many vectors are in that list? That's actually the key. If little n is 10, how many vectors are in that list? 11. So we actually have n plus 1 vectors in that, and it's living on an n-dimensional or 10-dimensional vector space. So what do we know about those vectors? If we have 11 of them and they're in a 10-dimensional vector space, what do we know about those 11 vectors? They're linearly dependent, aren't they? So this list must be linearly dependent since it has length or number of vectors n plus 1, and the dimension of our underlying vector space V was little n. Thus, if we write 0 is equal to a sub 0 v plus a1 t v plus a sub 2 t squared v plus dot 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 plus a sub n t to the n v, what can we say about those a's? Because we know v, tv up to t to the nv are dependent, we can find some nonlinear we can find some non-zero a's to cause that to equal the 0 vector. Thus, if we write this equation, we can find a set of complex, let's say, a sub l's, and here's an important point, all of those coefficients or scalars are not all 0. That make this equation true. And similar to how we were playing with sort of ordering things in the previous proof, let's do something similar here. Let's select little m, Michigan, different from n, Nevada. So let's let m be the largest integer such that a sub m is not equal to 0. So we're saying that some of those a's may turn out to be 0, but we know that some of them are not, and we've now ordered this such that a sub m is the largest integer that's not equal to 0. Going back to our labeling or numbers, we said little n was 10, didn't we? So maybe m is 6. Maybe a7, a8, a9, a10 are all 0. That's what this is saying. So let m be the largest integer such that a sub m is not equal to 0. We made a definite call on v. We said v wasn't the 0 vector. So since v was not equal to 0, then a1, a2, up to a sub m, those can't all be 0. We've already thrown away all the a's beyond little m, or beyond Michigan, but now we're saying that this set has to contain some that are non-zero. Since v was not equal to 0, a1, a2, up to a sub m cannot all be 0. Since that so here I'm saying a1, a2, a sub m cannot all be 0, since that would force a sub 0 to equal 0. Since we're saying that that combination is 0, and if a1 through a sub m were 0, then we would have a sub 0, v is 0, and we know v is non-zero. So if all those a1 through am are 0, that would force a sub 0 to be 0. And we know that can't be true, since that would force a sub 0 to equal 0. And we know the n plus 1 vectors are linearly dependent. That now says that Michigan, or little m, is strictly bigger than 0. Because we said a1 through a sub m can't all be 0. So one of those has to be non-zero. So this is now a strict inequality. But now that we have m bigger than 0, we can create a polynomial out of those coefficients, those a sub j's. We can use the a sub j's to write a polynomial where that polynomial now is, let's say, p of z equaling a sub 0 plus a1z plus a sub 2z squared plus a sub m z sub n. Or we could just keep going up to the a sub n. Let's go ahead and do that. And if they're 0, they're 0. But let's just say that this we can do. We have all of those a sub n's or a sub j's. But what do we know about a polynomial of nth order? We can find a root, can't we? So from chapter 4, any polynomial of order n with complex coefficients has n complex roots, and can be factored into n terms. By having m bigger than 0, then we know that we have at least a z on the right. It's not just a constant, that polynomial. It's more than just a sub 0, and that's what we need from chapter 4. So now we have this polynomial of order n with complex coefficients. We know that it has n complex roots, and so we can factor it into these n factors. And that's not true for a polynomial over the reals. Not true for real polynomials. Thought maybe switching colors would help, but it's getting tired just like we are. So now let's look at what that gives us. I'm not sure why I did that, but I thought it might wake it up, but I'm not sure I should have done that, but let's see what happens. So now we're wanting to factor this polynomial, p of z, into, let's say, a constant and these n factors, n minus lambda 1, or I'm sorry, z minus lambda 1, z minus lambda sub 2, up to z minus lambda sub n. We know we can do that. And in fact, since some of those coefficients were actually 0, let's just assume that those gave us 0 roots. So we had m was the highest power that was non-zero. So let's just go up to that particular order for this factor of polynomial. I have non-erasable ink, so I can add another hump. Luckily, I didn't do an m, trying to convert it to an n. So let's now do this. Okay? So let's now return to the polynomial. In our linear operator t, which says that we can now write that as 0 is equal to a sub 0 v plus a1 tv plus a sub 2 t squared v plus dot 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 plus a sub n t to the n v. And via additivity, we're actually able to write this as this 0 is equal to a sub 0 I plus a1t plus a sub 2 t squared plus dot 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 plus a sub n t to the n v. So maybe what I did want to do, but I hate to go back there, is go ahead and label that as n before, but I'm not going to do that. I'll do that after the fact. So now this particular polynomial in our operator this polynomial is really just p of t. You guys are having as much fun with this as the computer is, aren't you? But this is just p of t. And what can we do with that polynomial? Now it can be factored, can't it? So now we can factor that as 0 is equal to c, t minus lambda 1i, t minus lambda sub 2i, and we said that we only had m of those factors that were non-zero, so that's now there. We factored our polynomial in our linear operator t. But what does that actually mean? If that collection of factors, v was non-zero, c was non-zero, but somewhere along there we have to end up with a 0 for that right-hand side. What does that mean about that expression? What can we say about one or more of those factors, or can we say anything? What do we know has to be true? If that product of factors has to end up eventually giving us the 0 vector, something has to have a null space, a non-zero null space, doesn't it? Which means that one of those factors is non-injective, which means t minus lambda sub j I one of those is not an injective for at least one lambda sub j. Or that is t minus lambda sub j I has a non-trivial null space. But if t minus lambda sub j I has a non-trivial null space, what does that mean about that linear operator? Or think back about how we essentially started chapter 5. What did we need when we were trying to find eigenvectors? We tried to find a vector that was in the null space of something like this. T minus lambda sub j I had a non-trivial null space. So now we found that t, this linear operator, if this expression for lambda sub j has a non-trivial null space, that lambda sub j must be an eigenvalue. And that's what we set out to show. that given any linear operator on a finite dimensional complex vector space, that linear operator has a or an eigenvalue. Therefore, T has at least why am I tempting fate? I may just stop at that point, but I could do this. Why, I have no idea, but let me just try. T has at least one eigenvalue. And I will say that that's where we will stop. So that's now what we were able to conclude from this discussion. We were saying that this factored form of that polynomial in T had to be 0, which means that one of those factors has to have a non-trivial null space, or one of those factors has to be non-injective. And if that's the case, then we have found at least one eigenvalue for that linear operator. And we'll pick up at that point on Monday.